season starts here, the Vancouver Boat Show.
Welcome to the Vancouver International Boat Show virtual seminar series, sponsored by Freedom Marine International Yacht Sales, the premier choice for exploring the passion of yachting. Thank you for joining us. The seminar will begin in 1 moment. If you are having technical difficulties, you can reach me, the online moderator, via the chat feature at the bottom of your screen. Questions for the speaker can be added to the Q&A box also at the bottom of your screen. We will answer these at the end of the presentation. Now it is our pleasure to present Concepts of Celestial Navigation with Dominique Brunet. Welcome. Take it away.
Thank you. I'm Dominique Brunet. Thank you for being here. A full course on celestial navigation takes about 8 sessions of 3 hours, but I was told that you were particularly smart and you could digest it all in about 40 minutes, so that's what we'll do. And I can tell you that celestial navigation works because I used to fly commercially. I flew around the Arctic in the 60s, and I was navigating with an astral compass and the sight reduction table, and I'm still around. I found my way around. And then I was an instructor, a sailing instructor for 15 years or so until recently. And I taught celestial navigation and tried it myself. I crossed the Atlantic with it, and we found Guadeloupe, which is exactly where we were hoping to go. So it does work. But I'm going to give you today is an outline of the general principles of celestial navigation so that you get a feeling for how it works. So here is the plan for today. We're going to be measuring the angles of the sun, the moon, the celestial bodies above the horizon with various instruments. And then we're going to learn how to measure the latitude, which people have been doing for thousands of years, including those crossing the Sahara Desert with a camel, for instance, or those sailing along the Mediterranean, or Magellan, or Christopher Columbus. They navigated all by latitude only, by taking a sight on the sun at noon or taking a sight on Polaris at dawn and in the evening. And finally, we'll talk about measuring longitude, and that's a modern concept because it requires a system to keep track of the time and know around the Earth the exact time at Greenwich. So that requires a clock, and that was only invented a couple of 100 years ago. And then we'll say just a quick work on a general case when we want to take sight in the morning or in the afternoon rather than at dawn or at noon. So why do we need celestial navigation? That's because most of the travel around the world is over water and beyond the horizon. So we have no land reference. So we need to go by the stars. We're going to assume that the system is the one designed or explained by Ptolemy about 2,000 years ago. It's well proven. It's been used for 2,000 years. It works. And it says that the Earth is at the center of the universe, as you all know, and that everything turns around the Earth, including the planets and the sun. I've heard rumors that there's a new theory saying that the system, the real world, is built another way, but we're not going to use the new system. We're going to stick to the old one because it does the job for us. So how to measure the angles of the celestial body above the horizon, which is what gives us our latitude and eventually with a timepiece, our longitude. The first way was to use the cross staff. And you see what happens. You have a staff with a bar across it, and you can slide the bar along the staff and adjust it so that one tip is on the horizon and the other tip is in line with the celestial object. Usually it's the sun. So this is what happens when the first explorers were leaving Spain or Portugal to cross the Atlantic and look for the Caribbean. Here is the navigator before he departs. Here is the navigator after using the cross staff for a month or 6 weeks across the ocean and looking directly at the sun. And then when the navigator comes back to Portugal, this is what he looks like. So he's out of a job. And so another system was invented, which is called the backstaff. So the system is the same. Sorry. The system is the same using the staff and the cross bar, which slides. And instead of looking at the sun, you look at the shadow of the sun and you slide it along the bar and measure the angle this way. That was followed by the astrolabe that the Arabs used to cross the desert and to sail across the Mediterranean and offshore out of Africa. And this is very clever because it doesn't require a horizon since it's held vertically, because you suspend it or you hold it with 2 fingers. And then you aim at you put your eye on one side and aim at the celestial object, and usually the sun, through this diameter. And again, you burn your eyeballs, but that's the cost of knowing where you are. So that's the astrolabe around the 1500s. And then the version which ultimately prevailed is the sextant. It's called sextant, not because it has anything to do with sex, but because it's a sixth of a circle. So this is 60 degrees. And since you can read an angle which is twice as much, you can read angles of 120 degrees. So this is a sixth of a circle. And you put your eye in front of the eyepiece, and through the eyepiece, you can see directly on the side of the mirror here, next to the mirror, you can see directly towards the horizon. The sextant is held so that you can look at the horizon next to the mirror. And on the mirror, which is on the right-hand side of this area of the sextant, you can see a reflection of the sun on what is called the index mirror. And that's so that if the sun is up here, the rays of the sun bounce on this one, on that one, and into your eyepiece, and you can see the horizon. So when you can put next to each other the image of the horizon and the image of the sun, then you can measure directly the angle on the quadrant. So here is how it works. Here is your eyeball, and you can see right next to the mirror directly towards the horizon. And next to it, you can see the mirror in which you see the image of the sun reflected here. And what you see in the eyepiece is to the left, away from the sextant, the half which has nothing on which, through which you can see the horizon. And in the mirror, you can see the reflection of the sun. So the whole trick is to adjust the index. You move the index so this mirror moves until you can bring the celestial object, usually the sun, right on the horizon. And then you can measure directly the angle between the sun and the horizon. So that's how to measure the angles. Now, how do you determine your latitude? Well, for literally thousands of years, people have navigated across the desert and across the Mediterranean and across the Indian Ocean or the Pacific Ocean by taking a sight of the sun at noon. And that determines your latitude. Here is the equator, and the noon sight allows you to measure your latitude north or south of the equator. And the latitude is just the zenith of angle of the sun at noon. In other words, if you take a sight of the sun, say the sun is at 30 degrees above the horizon at noon where you are, then your latitude is the complementary angle between the sun and the vertical, where you can't measure unless you have an astrolabe which you hang with your hand, but you can't measure the angle between the vertical and the sun. So what you measure is the angle between the horizon and the sun, and you take 90 degrees minus that, and that gives you the zenith angle, and that's your latitude. It's only true when the sun is above the equator, but because of the tilt of the Earth, the sun moves a little bit north and a little bit south of the equator, depending on the season. So you have to make a little adjustment and correct for the latitude of the sun north or south of the equator, which everybody has known for hundreds of years, and which is drawn on charts, and even on the globes you have the declination of the sun throughout the year. So that's just a matter of adding or subtracting, depending on the time of year, the latitude of the sun. But otherwise, the latitude is just the zenith angle between the vertical and the sun. And it works, for instance, exactly without any correction at the time of the equinox on the 22nd of March and the 22nd of September. Then the sun is right above the equator, and you can get your latitude directly. Another way of doing it, so that's how Christopher Columbus and Magellan and all these guys were traveling. They'd go to a certain latitude and keep there by taking a sight at noon every day and maintaining this latitude until they hit land. They had no idea how far off they were, but by going along the same parallel, they were sure to get there eventually. And you can also tell your latitude by a sight of Polaris. Well, that's even easier, because if you take a sight on the northern star, your latitude is the angle that you measure. That's the altitude of the star above the horizon. So you measure a certain altitude above the horizon. That's what you measure with a sextant, and that's your latitude directly. There is no correction. And I've done that with students. I had sometimes students coming, and we were overnighting up and down the coast. And at dawn, when you can see already the horizon, or at dusk, when you can still see the horizon and the polar star at the same time, you just measure the angle between the horizon and the polar star, and that's your latitude. That's it, no correction. So you can't go wrong. So this is how people were crossing the oceans in the early days, a few hundred years ago. They took a sight at dawn on the polar star, at noon on the sun, and at dusk on the polar star, and kept on going through the night. And that allowed them to continue along the latitude which they wanted to follow to get to the land that they had discovered before, and they knew that it was at that latitude. So the latitude by Polaris is just the height of Polaris, or its altitude above the horizon. That's your latitude. Now, the problem of time. To know your longitude, you have to know at what time it is Greenwich time, wherever you are, in Africa or in America or in India. You have to know the time at Greenwich, because you know that the sun crosses the Greenwich meridian at noon. And from then on, the sun, so here are your meridians of longitude from 0 to 360 degrees going west. There's no east or west, luckily for celestial navigation. It's just 0 to 360 degrees going west from Greenwich. So the sun turns around the Earth. I told you we're using the old system. Turns around the Earth at 15 degrees per hour. That's 360 degrees per day. So in 24 hours, 360 degrees, the sun comes back to where it was a day ago. That's 360 degrees in 24 hours. That's 15 degrees per hour. So if the sun crosses Greenwich at noon, then at 1 o'clock Greenwich time, it'll be 15 degrees west. And at 2 o'clock Greenwich time, it'll be 30 degrees west, etc. So when you see the sun go by and is straight south of you, in other words, the sun crosses your own meridian, it's not over your head because you're not at the equator, but the sun is straight south of you. If you know the time in Greenwich, and you see the sun right as high as it gets during the day at the top of its apparent curve, then you say, it's 8 p.m. in Greenwich. So the sun has been traveling from noon to 8 p.m. at 15 degrees per hour. So that's 120 degrees. So your longitude is 120 degrees, and that's all there is to it. So the longitude is the time difference between the local noon where you are and the noon at Greenwich at 15 degrees per hour. That's how it's done. So that was that came about when there was an expedition by the British down to France. And I'm not going to tell you about the British, but you know what they've been doing to the French for the last 1,000 years or more, starting from taking the wine and from the Bordeaux area to burning Joan of Arc to sinking the French ships at Trafalgar. And so that day they went out, they had nothing to do, so they decided we'll go around the French coast and look for French ships to sink, just for fun. And so they did that, but the French were smart and they all hid away into the local harbor. So they went all the way down the French coast, couldn't find a French ship to sink. So they said, well, let's continue over Spain and see if we can sink some Spanish boats. They're not as fun to sink at, and they're probably rather more dangerous than the French boat, but still. So they did sink a few Spanish ships, and then they came back to celebrate at Portsmouth and have a beer. So by the time they came back, they were around here and not too sure. They knew their latitude, but they were not too sure about their longitude. Here is the end of Cornwall and the Scilly Island. So they had a powwow and they decided they were probably east, so it was okay to go east. Well, in fact, they were west, so they crashed into the Isles of Scilly, and this is what the Isles looked like, and it was an absolute disaster. And 300 years later, the French are still laughing about it. Anyhow, this is the fleet before the Scilly disaster, and this is the painting of the Scilly disaster. Well, British fleet was sunk or partially sunk. Anyhow, so some people in the Navy got mad and said, we've got to do something about it. And they produced the Longitude Act of 1714 as a result of this accident under Queen Anne. And decided that the problem of longitude was a problem of time. And the question is, how do you tell the time? And what time is it when the sun crosses your own meridian? That means the sun is at the top of its curve at noon. Locally, it crosses your meridian. What is the time at Greenwich? So how many hours has the sun been traveling at 15 degrees per hour? So the two approaches to measure the time by astronomers using celestial table and by mechanics who wanted to use the chronometer. So here's the meridian of Greenwich. And the time can be measured from the heavens because you have tables which indicate the distance between the moon and various stars. And the moon turns, and that's the only one which actually works along the model, as you know. The moon actually turns around the Earth in 30 days. That's 360 degrees around the Earth in 30 days. So that's 12 degrees per 24 hours, which is 30 minutes per hour, or 1 minute of angle in 2 minutes of time. Well, 1 minute of angle can be measured with a sextant. So if you arrive in a foreign land and can set up an observatory on land and do the measurements of the distance between the moon and some stars, which are in the tables, then eventually you can calculate the time where you are and adjust your timepiece accordingly. Apparently, the calculation take about 6 hours, but it can be done, and you get a precision no matter how far away you are from Greenwich. Eventually, you get a time with a precision of about 2 minutes. So that's quite useful. You could also get the time from the tables giving you the position of the satellites of Jupiter, but of course, you're going to be able to see Jupiter. This is Galileo's representation of Jupiter, and here you can see 2 satellites, and he said at some other time you could see 4, and then you could see 4. So from these measures, it is deducted, it concluded that there were 4 satellites of Jupiter, and they've been used to measure the time because you've got tables giving you the position of the satellite of Jupiter, depending on the day of the year, if you can tell one satellite from the other. Now, the second approach was to use a mechanical system. That's Harrison. You may have seen a series on television called Longitude, and the 50 years of his life that Harrison spent building chronometers. This is his final version. It's Harrison 4, chronometer number 4, which was tested by Cook, who came back absolutely thrilled. He went across the Pacific and then halfway around the world and came back absolutely thrilled, because with this chronometer, for the first time in his life, he knew where he was. And every month or so, he'd set up an observatory on land and calculate the time from the satellite of Jupiter or from the moon and adjust his chronometer a little bit. But it was good for several weeks without much of an error. Now, so that's for the latitude at dawn, at dusk, and at noon, and that's for the longitude with the chronometer. When you take a site anytime in the morning or in the afternoon, you take advantage of the fact that the Earth is round. So this is the vertical axis of rotation of the Earth, and this is the sun geographic position. That means that the sun is right above this point on Earth at the time when you take the sight. And we know that because there is a book called the Almanac, and here is the Almanac. And for every day, you've got pages of calculation giving you the time of day for one day, the next day, and the third day, for the double pages for 3 days. And you've got the planets on one side and the sun and the moon on the other page, and the stars in between. So it tells you the latitude and the longitude of the point on Earth over which the sun is, or the moon, or the planet, or whatever you're looking for. It tells you exactly where you have to be on Earth so that whatever you're looking at is exactly above you. So that's a geographic position, for instance, in this case, of the sun. So you can tell that for years in advance with a high degree of precision, because it's very well established and calculated in advance. So you know where the geographic position is, and depending on how far you are from the geographic position, the angle at which you see the sun gets smaller and smaller. So knowing this angle, you can draw the circle of position. That's where you are. So you have to know the geographic position, which you do from the almanac, and then you have to measure this angle with the sextant, the angle of the sun, for instance, above the horizon. And from this angle, and it's very easy to do, you can draw your circle of position. And how do you do that? Well, you know that here, if the body is here, here is the angle that you measure with a sextant. And the zenith angle is the complementary angle. And that's the angle at the center of the Earth. It's the same angle. And you remember from your navigation courses and the definition of the nautical mile, that a nautical mile on the surface of the Earth is equivalent to 1 minute of angle at the center of the Earth. So 1 degree is 60 nautical miles. 1 degree of angle on the Earth is 60 nautical miles on the surface. So what you do is you measure h with a sextant, you calculate 90 degrees minus h to get the angle at the center of the Earth, and you multiply that angle by 60, and it gives you the radius of the circle that is centered around the sun geographic position. So you take a site, for instance, here at 9 o'clock in the morning, and the sun is somewhere on Earth, which you determine from the almanac. You know exactly where it is, and you measure your angle, and you draw a circle of position. And then assuming you haven't moved too much, and if you move, that's okay. You just move the first circle of position by the distance you've traveled, so there's nothing to it. But if you're at anchor, for instance, so you take your morning sight, and in the afternoon, the sun has moved west. It is now, say, over Hawaii. Maybe this was over Cuba, and now it's over Hawaii at 4 o'clock in the afternoon, for instance. You take another sight, a second circle of position, and that gives you your position. So I'm going to give you an example. So the coordinates of the geographic position of the center of the circle of position is provided by the nautical almanac. So example, on May the 16th, in the morning and the afternoon, we take 2 sites. So this is a page of the nautical almanac. So in the morning, say we're somewhere around here, I look at my watch giving me my time in Greenwich, and it's 1700 UTC on May the 16th. So in the almanac, I look at the page for May 16, 18. Here is the 16th. So this would be the 17th. So this, and these are the hours in Greenwich time. So at 1700, which is morning for me, 1700, the sun is 75 degrees west of Greenwich. Well, that sounds about right, because at noon at Greenwich, the sun was right above the Greenwich. And at 1 o'clock, it's at 15 degrees west, 30 degrees, 40. So at 5 o'clock in the evening, it's 75 degrees west. And what is, in a few minutes, and what is the longitude, the latitude of the sun? It's north 19 degrees, because it's in May. So the sun is in the northern hemisphere, and it travels between the equator and the tropics. The tropics are at 23. So in May, it's below 23 degrees latitude north. It's at 19. That makes a lot of sense. So this is the position of the sun. This is the position of the sun over the earth, its longitude and its latitude. So the sun is over Guantanamo, Cuba. This is the longitude and latitude of the sun. It's over Guantanamo, so we plot it. And I didn't choose Guantanamo on purpose. It just happens to be this way. So here is the sun and measure. So at noon, when I took my sight, wherever I am here in the Pacific somewhere, I took my sight in the morning, and the sun, when I took my sun, was right over here. Now the second measure is this. I take a sight of the sun in the morning, and I found that the sun is at 39 degrees above the horizon. So the zenith distance, 90 degrees minus that's the angle above me, is 51 degrees. So that's the zenith angle, which is the same as the angle at the center of the earth. So what is my radius? It's 51 degrees times 60 nautical miles per degree, 3,000 nautical miles. So here is the center of my circle. And on the sphere, rather than the map, the big sphere, I draw a circle of 3,060 nautical miles, and I get this circular position. So that's in the morning. So in the morning, I must be here somewhere. The sun is to the southeast. That makes sense. Now, in the afternoon, I look at my watch for Greenwich. It's already 10 o'clock at night. Well, at 10 o'clock at night, the sun has been traveling for 10 hours since noon. So it has traveled 150 degrees west. So that's the longitude of the sun, 150 degrees and some minutes. And it's still essentially at the same latitude, because that's the latitude of the sun at that time of the year. So the sun is over a point somewhere in Hawaii. So we plot it. And then what about the angle? We measure the angle at 55 degrees. So the zenith angle between the vertical and the sun is 90 minus 55. And that's 35. And so the radius of the circle, that's the center of the earth, 35 degrees times 60 nautical miles per degree, 2,100 nautical miles. So here is my second circular position. The sun is over Hawaii, the same latitude, same declination, essentially. It's over Hawaii. And the radius is a couple thousand nautical miles. I draw it. And this is my afternoon circular position. Are you going to say, well, I don't know if I'm here or there? Well, if you don't know, you shouldn't be navigating. So assume that you have an idea of where you are. And so this is if you blew up the drawing, this is what you get, the intersection. And I don't know exactly where that is. Where you see? Granville Bridge, Burrard Bridge, PC. Ah, that's a boat show. Well, so that's a very precise measure. That's quite remarkable. So that was indeed taken from the boat show, and that's exactly where you are. Now, the last couple of slides I want to tell you is how to, in fact, zoom in as I just did to get better precision. It's called the Mark Saint-Hilaire method. And I'm not going to go into it details because it's just very, very clever. It's very smart. It uses the site reduction tables. So the site reduction tables give you numbers galore. And the full McCoy has 7 volumes. It's that thick. And this is what you get. You know, it's not very thrilling reading, but each book is 250 pages. You got 7 books of that. But most people use the abridged version, which is good enough for navigators, which are specifically designed for pilots, because pilots are not very clever. I know because I was one. So if it's too complicated, they don't understand. And that's more than enough. And with 2 books, you can travel around the world with a sextant or with an airplane. This is what I was doing when I was in the Arctic, taking sites on the sun or on the moon or on the planets, using the same site reduction table specifically said for, it says on the American version of it, that it's for aviators or pilots, in other words, for dummies. So here is it, and that's my last slide. Here is what it does. It pre-calculates the angle at which you will see the sun, wherever the sun is on Earth, and wherever you are on Earth from a place where you can see the sun. In other words, all those millions and millions and tens of millions of numbers tell you at what altitude above the horizon you should see the sun if the sun is here and you're over there. Now, you know exactly where the sun is because that's in the almanac. What about your own position? Well, you don't know your position, so you assume that you are in that neighborhood somewhere. And what you do is you look at the table and see at what angle you should see the sun if you were here. And that's the height calculated, HC, it's calculated from the book. So you tell the book the position of the sun, the geographic position of the sun. You tell the book what your assumed position is, and the book tells you instantly that you should see the sun at 17 degrees and 25 minutes above the horizon. That's what you, if you were there. But you actually measure not 17 degrees 25, but 17 degrees 21 minutes. So the angle at which you see the sun is a bit smaller. So you're not here, you're a bit further. And because it's the same angle as the center of the Earth, there's a 4-minute difference. So you're 44 nautical miles further away than the sun. So now you know that your line of position or your segment of position is at 90 degrees from the direction of the sun, because that's given to you in the table also. They tell you exactly what direction the sun is. So you extend it and you draw a line, and that's your line of position. And that's just very smart. And with that, it's a piece of cake. So that's the end of my presentation. I just wanted to tell you that all the juicy details are available in this book called Celestial Navigation. I mentioned here, as will be seen in the French exhibit. By the way, the film, I hear it just came out a few days ago, and I got a call about a year ago from New York with a filmmaker. I thought it was a joke. He said, "Look, we'd like to use your book for a new film that we're starting to produce with Michelle Pfeiffer and some other famous actors. I don't know. It's about the crossing of the North Atlantic on some big ship in 1920s, like the Queen Mary or something like that. And I said, well, you can't make a film out of a celestial navigation book. It's nothing but, it's unreadable, and secondly, it's nothing but numbers and digits and graphs and tables. It's awful. So he said, well, we're not interested in the content. We like the cover. So can we use the cover in the film? I say, sure. And where are you going to use it? Well, he said, there's a scene, or there are two scenes, which happen in the wheelhouse, in that big Queen Mary reconstruction or some other similar ship. And so it'll be on the chart table. And I said, well, what I'd like you to do now, if you're going to use my book, is ask Michelle Pfeiffer to come in with the captain, and which is what happened. She comes to the wheelhouse with the captain, and the book must be around there. So I haven't seen the film. And I'd like Michelle Pfeiffer to pick up the book and show it on the screen and say, oh, Captain, I noticed you have this fabulous book on celestial navigation by Dominic Preeney. This is a wonderful book, and I have it on my bookshelf, and I would recommend it to all my friends. But then the guy in New York told me, but the script had been finished, and they're not going to change the script. So I don't even know whether the book appears or not in the film, but I thought it was an amusing story when it happened. And there's a companion book, which is called The Celestial Navigation Exercise. There are also two books. That's my minute of advertising. Coastal Navigation and Coastal Navigation Exercises. And that's available from Amazon and the big retailers, or from the publisher. And now the last thing I want to tell you, this flying, which I was doing in the 60s, now has resulted in a book of wild and wonderful adventures. And that flight, that picture is taken at latitude 80 degrees north in the middle of February, 50 below in temperature. And the passengers, it was so cold inside the airplane that the passenger sent to me a bottle of whiskey. And I thought it was a nice gesture because I was peeing in my pants. I was so terrorized. We flew up there for a week, and it was just awful in the dark. And so I thought they wanted to cheer me up, but just wanted to show me that the whiskey was frozen in the bottle inside the airplane. And we landed on the ice cap, and it was just awful. So I just came out a few days ago. Anyhow, that's the end of my story. Thank you very much. I'm available for questions. And you can reach me at this email address. Any questions?
All right, perfect. If you have any questions for Dominique, make sure to drop them into the Q&A box at the bottom of the screen. To start us off, what is the map projection of the world map used with the almanac tables?
Does
that make sense?
Yeah, it makes sense. And the answer is that I've never thought of it, and I don't know. I think the precision is very accurate. They must have used a sphere, and in fact, they must have used what is called a WGS 84, the World Geodesic Survey of 1984, which is a new survey used by the GPS, which assumes that the Earth is a sphere and adjusts all the coordinates accordingly. So as of fairly recently, the last 10 or 20 years, the coordinates are exact because they've been corrected in line with this World Geodesic Survey. And so it doesn't depend on the projection.
All right, next up here, are there any online versions of all the tables you have mentioned?
Yes, absolutely. They're all free, and you can buy them or you can download them in PDF. And when you go on a boat trip, you put it on a DVD and stick it in your computer. But it's safer to have a book version. So you have the book version and the PDF version of all these tables, and they're all free.
Perfect. Ross asks, the Earth is not a perfect sphere. The nautical almanac in the early 1800s did not take this into account, leading to errors in measured positions by early surveyors. When was the almanac corrected to reflect the actual shape of the Earth?
Well, I suspect that it was a result of the World Geodesic Survey of 1984, which standardized the latitude and longitude for all countries and all charts based on this one reference. And that would have happened after 1984. And now all the charts around the world use the same reference, and you no longer have to adjust your GPS depending on the chart that you use. Because in the old days, when you go to a foreign country and start using a different type of chart, you have to adjust your GPS to the horizontal datum for the chart type that you're using. And I know from experience that when about 20 years ago, I was sailing along the south coast of Turkey using, I think, German charts, which are the only ones available at the time. And I was off by several hundred meters every time I was trying to get into a harbor at night, and it was hard to find. I couldn't find it because I had failed to adjust my GPS to the local chart horizontal datum. And that taught me a lesson that I haven't forgotten. But now the problem has disappeared. Everybody uses the WGS 84 datum from 1984.
All right, next up, Martin asks, have you used Weems tables for sight reduction? Do you teach this method?
I've never used it, and I think the method is in the back of the book. In the back of the book, there are I explain how to use some other sight reduction tables. The ones I've shown you here are the most common one used pretty well around the Earth. And but there are others which are supposedly simpler, but I found them rather complicated, in fact. So I'm used to those ones, and those are very straightforward. In fact, in the book, you have tables, or you have blank tables, which guide you step by step all the way through the calculation. You just pick up the numbers from here and there from that table, etc., and you do your calculation, and you don't even have to think about it. But I train my students to do it without the table on the back of an envelope, so they really understand the system. And yeah, so yes, I think at the back of the book, I describe, this is one of the systems that I also describe.
All right, Keith asks, what make model of sextant of quality do you recommend for offshore journeys?
You need a simple sextant. You don't need anything fancy metal at $1,000 or $1,500. You need a plastic model, not the very basic one, which is flat in plastic. It's too primitive, but you use the $250 model, which is plenty good enough. The problem is not the precision of the sextant. The problem is the precision of the measures that you take, and in particular, taking the vertical, when you have to measure the vertical distance between the sun, for instance, and the horizon, and it's easy to tilt the sextant and measure an angle which is bigger than the real one. So you have to swing your sextant and keep the sun tangent to the horizon, and that's the tricky part. So you don't need a sophisticated sextant, just a $250 one, or cheaper secondhand, because a lot of people no longer need their sextant, but that's what it, plastic is good enough.
All right. Christina asks, please help me understand the difference between true north and the North Star. I'm boating in the Vancouver and British Columbia area, Canada.
The North Star is very close to the true north. The difference is at most about a degree or a degree and a half. And so normally you go by the North Star if you want the north. If you want to make the corrections are available in the Nautical Almanac. But it's a small correction, and you can negate the correction by taking a sight on the North Star for your direction only, not your latitude. If you take a sight of the North Star at dawn and then another one at dusk, at 12 hours difference, and you take the average of the direction, that's exactly the north, because the North Star describes a tiny little circle about, I think it's 1.2 degrees of radius, a tiny little circle. So if you take a shot at dawn and at dusk in opposite sides, and you take the average, that's your true north.
Perfect. Where can you get sextants repaired?
I don't know. Sorry, I don't know. You'd have to do a search on the web. I don't know.
Yeah, fair enough. We have a few people asking where they can find your celestial navigation book.
You buy it off the web. You buy it off the web, or you buy it off Friesen Press. Friesen Press is here in Victoria, and you can order them from them or from Amazon, from those large retailers, and you can get a version for a tablet. I wouldn't recommend the version for the tablet because you really have to be able to do exercises and follow the samples and have a pencil and flip through the pages. So Amazon, large retailers, or the publisher in Victoria, Friesen Press. And it's cheap, 25 bucks, I think. Took me 15 years to put it together, so it's a good price.
All right, I have a question here regarding doing a Sail Canada celestial navigation. Do you know what is the Sail Canada working sheets we must use? I'm really hoping we can use your working sheets for the Sail Canada exam.
Yes, the celestial navigation book and the exercise book are designed, because I used to be teaching the Sail Canada program and prepare students for that program. And some instructors still teaching the stuff use my book. So it's specifically designed for the Sail Canada program. And on the Sail Canada program, you use whatever sheets you want, and you can, the sheets are available to be downloaded for free from my website, or you can copy them from the book. There are some blank sheets. You can use that, and in your calculation, you attach your working sheets to the test. And by the way, the test can be prepared by doing the review exercises at the end of the exercise book. It prepares you directly for the Sail Canada test. And if you don't have 110% with that, then there's something wrong with you, because it's explained in great details, and it takes you by the hand, and it's essentially the test itself.
All right, perfect. I think that brings us to the end of our questions here. Before we wrap up today, is there anything you would like to add?
No, I hope you enjoy it and you can follow it. I'm available for support, and then my time is free. Given my age, I have no opportunity cost, and So I do that once in a while. 2 or 3 months ago, I got a 1-hour phone call from a guy in New York who wanted to get some explanation. And then a few months before, I had another call from somebody very far who wanted, and I've had coffee with people. They buy the coffee and I provide the support. Or you can contact me by phone or by email. My time is free and I'm available to help. And even if you don't use it in practice, the concept, especially the last bit, the Marc Saint-Hilaire method, is just very clever, and it's a joy to think of the method to find your way from the stars and the celestial bodies, find your way around the Earth. It's absolutely fascinating. Even if you don't use it in practice, just understand, just like learning a language. It's absolutely fascinating. The concept is just very clever. Thank you.
All right, thank you very much. I want to thank Dominique for your time here today, and I want to thank everyone at home for joining us as well. We're interested in your feedback either on this seminar or if you have any ideas on topics you would like to see us cover in the future. So simply click on the Evaluate tab located just above the seminar description and complete the form. After the show, all attendees will also receive a post-show survey. Be sure to check out all the features at VIBS Virtual. If you have any questions, you can check out the info booth for answers. And I hope you all enjoy the rest of your day here at the Boat Show. I also wanted to thank our sponsor quickly, Freedom Marine International Yacht Sales. And I hope you all enjoy the rest of your time. Take care.
Bye-bye. Thank you.
Oh yeah, the season starts here. The